Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about what is a photon, and also the related question of what is light? Is light a particle or a wave? Classically, light is a wave. It is a wave in the electric and magnetic fields, and it has polarization, and it propagates at the speed of light. And it carries energy with it, which is proportional to the square of the amplitude of the electric field. And one of the compelling pieces of evidence to indicate that light, in the classical view, is a wave is the fact that it can exhibit interference effects. So you can build various kinds of interferometers. In this course, we'll talk about one particular design called the Mach-Zehnder interferometer. And the basic idea is you have a beam of light and you use these beam splitters. In Mach-Zehnder, there are two beam splitters to split the light and have it go along different paths, and then they get recombined at certain points. And what you find is that, say, the intensity of the light exiting here depends on effectively the difference in path between the two different possible choices. So you can introduce a variable phase difference in one of the paths, maybe by changing its length or by inserting a piece of glass or something, and you find these interference effects where the intensity of the light varies um, according to this mathematical expression here as a function of these phase differences. And so those interference effects seem like they're well explained by this classical view of light being a wave. And then quantum mechanics says not so fast. It's not so clear that light is a wave, the way classical physics says. If you deal with very weak beams of light, you notice that the amount of energy contained in the light is not a continuous quantity, but energy seems to come in packets of size h bar omega. So the energy comes in lumps. And if you put it, we have detectors here that can sort of respond to individual lumps of energy. And if you put the detector at point A here, you see the energy arriving in discrete packets or lumps of magnitude h bar omega. And not only that, but if you put detectors at points C or D, you get lumps, but when you get a lump at C, you never get a lump at D at the same time. And similarly, if you see a lump arriving at point D, there's not a lump arriving at point C. So it really seems like there's this particle-like aspect to light. And Einstein was coined the name photon to describe this particle-like aspect of light. So a photon is an example of a quantum particle. And as Feynman so eloquently puts it, quantum particles are like nothing that you have ever seen. Particle, they're neither exactly like a classical wave, nor are they exactly like a classical particle. They're sort of somewhere in between. And the words that we use, calling this a quantum particle, it's a little bit unfortunate because the fact that it has the word particle in the title sort of biases you into thinking it's a little bit more like a particle than a wave. But that's really just a matter of our language. When we say quantum particle, we mean something that is, in some sense, neither particle nor wave, or maybe a better way to say it is in some way both. But we struggle with the language here because the way quantum mechanics behaves is so unfamiliar to our everyday experience that our everyday experience doesn't really prepare us to deal with these concepts. And just a brief little history lesson, the idea of photons, there's a long history associated with it. It was really sort of, in some sense, present at the birth of quantum mechanics. If you go back to Planck's work with explaining the spectrum of blackbody radiation, Planck in 1900 introduced the idea that the energy in the electromagnetic waves were quantized in multiples of h bar omega. And just 5 years later, Einstein built on this idea. He coined the name photon to explain the photoelectric effect. And then it took another 20 years or so before Dirac introduced the beginnings of quantum field theory, a full quantum mechanical treatment of the electromagnetic field. And if you're interested, you can read about that work in chapter 16 of Beck. We won't be covering it. But really, the full-blown modern understanding of the quantum treatment of electromagnetism took until 1947 when Feynman, Schwinger, and Tominaga independently developed what's known as QED, quantum electrodynamics, which is an unbelievably successful theory of our understanding of the way light and matter interact with one another. But that is well beyond the scope of physics 323. So we won't get to quantum electrodynamics this term. So in physics 302, the quantum mechanical particle that you dealt with primarily was the electron. And in physics 323, we're going to tend to talk about photons more than electrons, in part because photons are actually experimentally much easier to deal with. We have a simple experimental way down in our laser lab of generating single photons and detecting single photons and manipulating the quantum mechanical state of a single photon. And we could also do that, it turns out, in the laser lab with things that are like electrons. These NG centers in diamond are more like electrons, but those are much harder experiments. So for a variety of reasons, we're going to focus more on photons than electrons in physics 323. And as Feynman memorably says, for a lot of purposes, electrons and photons are different quantum mechanical particles. They're screwy, but they're both screwy in exactly the same way. So what he means by that is that a lot of the experiments we're going to describe, you could equally well do, at least in principle, with either electrons or photons. But having said that, there are some important differences between electrons and photons, and it's worth cataloging them right now. So an electron is a charged particle. It has a charge, a negative charge, of course, of minus E, minus 1 elementary charge unit, or minus 1.6 times 10 to the minus 19 coulombs. Photons, on the other hand, have no charge. Electrons have mass. They don't have much mass, but they have mass, a mass which we typically call m sub e. And the mass of an electron is 9.1 times 10 to the minus 31, very small, but non-zero kilograms. Photons, on the other hand, have no mass. They are massless particles. And from your study of special relativity, you know that particles without mass can have energy, but they must travel at the speed of light. Massless particles like photons travel at the speed of light. And that's true for all observers. No matter who's observing a photon, their central postulate of relativity is that all observers will agree that photons travel at the speed of light. So that's a really important distinction between photons and electrons. Photons are inherently relativistic particles. You need relativity to describe photons correctly. They travel at the speed of light. Electrons with mass they can travel at any speed as long as it's less than the speed of light. They can move very slowly. They can be essentially at rest. Or close to at rest for observers. And so that's a really important distinction between electrons and photons. And the fact that electrons are not inherently relativistic particles means you can use a theory like the one you use in physics 302. The Schrodinger equation that you dealt with is not a relativistically correct expression, but as long as you're dealing with quantum mechanical particles like electrons that are moving at speeds that are small compared to the speed of light, you get very accurate, not perfectly accurate, but quite accurate results by using a non-relativistic theory like the one embodied by the Schrodinger equation. An important property of electrons, which you studied in Physics 302, is the fact that they have spin angular momentum. And the angular momentum associated with an electron is h bar over 2. So electrons are referred to as spin 1/2 particles. Or more specifically, if you measure the component of the spin angular momentum along any particular direction, you either get plus or minus h bar over 2. And the fact that the spin angular momentum associated with an electron is a half integer is very important. It means electrons are examples of what are called fermions, and that has important implications down the road. Photons, on the other hand, have an integral amount of spin. They're spin 1 particles. The spin angular momentum associated with a photon is h bar, 1 times h bar, and so that means photons are classified as bosons. And if you make measurements of the spin angular momentum of a photon, it'll have magnitude h bar, and it will either be directed along the direction in which the photon is moving or opposite to the direction of which the photon is moving. So the direction of the angular momentum has really one of two choices, either along the direction of propagation or not, or anti-parallel to the direction of propagation. Okay, and last but certainly not least, I'd like to talk about the concept of polarization as it relates to a photon. So when we talk about electromagnetic waves in a classical view, this is a view of a linearly polarized electromagnetic wave. So when we talk about polarization of classical waves, we focus on the direction of the electric field, and this wave is linearly polarized along the vertical direction, which in this diagram is being called the x direction. And if you read through the polarization tutorial, we have a long description of the different ways that you can, different sort of polarization states that classical electromagnetic waves can be in. They don't, there are other possibilities other than being linearly polarized. They can be circularly polarized. They can be elliptically polarized. And the question is, how do we deal with polarization on the quantum mechanical level when we're talking about single photons? Well, the short answer is that while the idea of polarization of a photon is a little bit more abstract than in the classical case, you can't really point to, a vector associated with an electric field that's pointing in a particular direction. A lot of the ideas for describing classical polarization really carry through to describing the polarization of a single photon. So we can talk about the polarization state of a photon, and we'll describe the polarization state of a linearly polarized photon this way. This is a vertically polarized photon, and it has a polarization state V, whereas circularly polarized light has a polarization state which is a linear combination of horizontally and vertically polarized light with a 90-degree phase difference between them. So we will play out these ideas over the course of this term, but the really nice idea is that a lot of the treatment for classical electromagnetic waves, a lot of the treatment of polarization of classical electromagnetic waves really carries through with only minor modifications to deal with polarization of a photon quantum mechanically. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.